Hello, and welcome to Section 5.5 on the Substitution Rule. In this section, we develop a rule for integration, which is analogous to the chain rule for differentiation. Recall, the chain rule gives us a way of differentiating functions that are the composition of simpler functions. If little f of x is the derivative of big f of x, the chain rule says that the derivative of big f of g of x is little f of g of x times g prime of x. This means that f of g of x is an antiderivative of little f of g of x times g prime of x. This observation is the basis for the substitution rule, which amounts to applying the chain rule in reverse. The substitution rule simply says, if u equals g of x is a differentiable function whose range is an interval I, and if f is a continuous function on I, then the integral of f of g of x times g prime of x dx is equal to the integral of f of u du. The key to using the substitution rule is identifying where it can be useful. Look for compositions where a function g is inside another function f, and where parts of the derivative of g exist under the integral. If this occurs, we may have a good substitution. For example, we can integrate the function 2x times sine of x squared. Notice that sine of x squared is a composition of the sine function and the function x squared. Moreover, 2x, the derivative of x squared, shows up in the integral. Let u equal x squared, then the differential du is equal to 2x dx. Making substitutions, we get the integral of sine of u du. This is something we know how to integrate. We get negative cosine of u plus c. Now back substituting, we obtain the solution. Negative cosine of x squared plus c. Another trick with substituting is to choose functions whose substitution leads directly to a function that can be integrated. For example, we can try and integrate 1 over 5 minus 3x squared. We can take the substitution u equal to 5 minus 3x. Then the differential du is equal to negative 3 dx. Dividing both sides by negative 3, we see that negative 1/3 du equals dx. Now making substitutions, we now instead need to integrate negative 1/3 times 1 over u squared, or negative 1/3 u to the negative 2. This gives 1/3 u to the negative 1 plus c, or 1 over 3u plus c. Back substituting, we obtain the solution, 1 over 3 times 5 minus 3x plus c. It is sometimes necessary to find clever ways while substituting to force all x variables into u variables. For example, we can take the integral x cubed times the square root of 1 plus x squared. In this example, the derivative of 1 plus x squared exists, but there will be 2 extra x's remaining. Fortunately, we can continue to use our substitution. Since u equals 1 plus x squared, we know that x squared equals u minus 1. Computing the differential, we see that du equals 2x dx. Using all three of these pieces of information, we can now make the appropriate substitutions to find a new integral. Now we are integrating 1/2 u minus 1 times u to the 1/2. Distributing, finding the antiderivatives, and simplifying, we arrive at 1/5 u to the 5/2 minus 1/3 u to the 3/2 plus c. Back substituting to complete the problem, we find 1/5 times 1 plus x squared to the 5/2 minus 1/3 times 1 plus x squared to the 3/2 plus c. You may have noticed that all three examples in this video have been indefinite integrals. The substitution rule also applies to definite integrals. However, there is an extra step which will be discussed in class. You've seen the basics, now work towards mastery through practice and study.